All right, so just two pieces of vocabulary. You're going to learn what an even function is and what an odd function is. And what it talks about is the symmetry of the graph. Symmetry is super helpful when you're graphing, because if you have symmetry, you get one point, you can find the symmetric point, and then it saves you work. So that's why it's a super helpful thing. So an even function is symmetric to the y-axis. So symmetric to the y-axis. So there's two ways you can do this. You just look at it and go, oh, I see the symmetry. Or if you don't have a graph, there's a test for that too. So graphically or algebraically. So a graph that's symmetric to the y-axis would be something like this. Which parent function is that? Quadratic. Now the parent function is symmetric to the y-axis. Would every single quadratic ever be symmetric to the y-axis? No, because you can take it and move it left or right, and then that symmetry goes out the window. But the parent function is. Now, if you don't have a graph, here's the test. You plug in negative x. And here's the thing. You don't try to force it to come out to be anything. It's a test. You see what happens. And if it equals exactly what you started with, you get back the exact same thing, then it's equal. All right, then we have odd function. Usually everyone's like, oh, that's symmetric to the x-axis. It can't be. Why can't you have symmetry to the x-axis? It's not a function. Okay, it's going to pass your, it's going to fail your vertical line test. So instead, odd means it is symmetric to the origin, which is helpful that odd starts with O and origin starts with O, just the way our language works. That's convenience. Symmetric to the origin. So that would be something like this. If you're just looking at it visually, do you remember your quadrants? It's probably been a while since you've talked about quadrants, but quadrant 1 goes down to quadrant 3, like it goes across the origin. Okay, cool. Thank you for heads on it. So symmetric to the origin. It's the same test. If you don't have a graph, you would plug in negative x, and if you get back the exact opposite of what you started with, and that's again convenient, odd, opposite. If you get back the exact opposite of what you started with, then it's odd. The trick with these is you can't try to force it to be something. People will have a preconceived notion and try to make it turn out even or make it turn out odd. You can't do that. You just have to like see what you've got. All right, so for this one, we're going to plug in negative x. That means everywhere that there is an x, you're going to put a negative x. And I say give it a hug, put parentheses around it. So everywhere that there was an x, you're going to put a negative x. And then you just see what happens. Hey, kiddos, if you take negative x and square it, you don't have to write this. I'm just going to show you. It would look like that. That's what squared means. I call it a twin. There's two of them. What's going to happen to the negatives there? And it will be positive, and x times x is x squared. The common mistake I get is that people lose the squared. There's still two of them. It's just the negatives canceled out. And then how about this second part? 5 times negative x. It'll be negative 5x. Now here's the other common mistake. I've been doing this for so long. I know exactly what the common mistakes are. Is people will write this. And I understand what you were trying to say, but I have to mark it wrong because what does this mean? 5 minus x, like subtraction, you have to put the negative in front. Okay, so don't do that. In fact, I'm going to erase that. That's very wrong. Don't do that. Okay. And then you look at what you ended up with and you compare it to the original problem. So, hey, look, the first term is the same. Do you see that? X squared, x squared. The second term is different. So the first one's the same and the second one's different. So it's not even or odd. It's neither. One term was the same and one was opposite. It has to be the whole thing together, all the same or all opposite. Let's try it again. If you plug in negative x, where there was an x, you're going to put a negative x and just give it a hug. Now, I don't want to write this out 6 times, but can you, in your imagination, picture negative x times negative x times negative x, like 6 of them? What's going to happen? It'll be positive, because if you have an even number of them, the negatives are all going to cancel. But again, the common mistake is people lose the 6. That's still there. You still have 6 x's. the negatives just canceled out. So this is what we ended up with. Then you compare that with what you started with. Here's what we started with. Here's what we ended up with. What do you notice? It's the same, so it is even. Same means even, odd means opposite. Let's try it again. Everywhere that there was an X, you're going to put a negative X and give them hugs. Parentheses around it. So again, I'm not going to write it 9 times, but in your imagination, picture a negative X times a negative X times a negative X 9 times. What's going to happen? It'll be negative because pairs will cancel, and then that odd one, you have an extra one. So it will be negative 4x to the 9th. Again, don't write this. The common mistake I get is people will write this. And again, I'm trying to hammer this hard so no one does this year. That means what? For minus, it's not subtraction. You have to take the negative and put it out front. Please don't do that. I'm saying it, but someone's going to do it. Like, it happens every year. All right, and then plus negative x would just be minus x. So then you compare with what you started with. Compare this with the original problem. What do you notice? The first term's opposite and the second term's opposite, so odd. Same means even, odd, or opposite means odd. If it's like a mixture, then it would be neither. And so let's just try one more. Everywhere there's an X, put a negative X and give them hugs. Actually, to do a compare and contrast, I made this the exact same problem we just did, except what did I throw in there? Yeah, I stuck a +2. These are the same problem. I just stuck a +2 in it. So it's going to be the exact same thing. Negative 4x to the 9th minus x plus 2. I just wanted to show you what throwing a 2 in there would do. If you throw in like a constant part, something that doesn't have an x with it. The first term is opposite. The second term is opposite, but this was a 2 and it's still a 2. So what do you think? Yeah, it'd be neither. These two terms are opposite, but the 2 is the same, so neither. So if you just throw a number in there, it kind of throws the whole thing off. Now, those are the ones that involved like work. These ones, we're just going to look at a graph. So you have to visually see where the symmetry is. So looking at this one, here's your y-axis. Do you see the symmetry to the y-axis? Okay, because like, do you see it is not really something that's teachable. I can't force you to see it, but I can show it to you. Do you see the symmetry here? Okay, like if you folded it in half. So which one is that? So even, good. How about this thing that looks like the Little Dipper? Yeah, there's no symmetry there, so neither. Do you remember which function this is? It's a piece of it. I'll be impressed if you remember. Sine, good. That's, oh my gosh, you guys are awesome. So it is symmetric to the origin. This piece up here in quadrant 1 went down to quadrant 3, so that would be odd. Now these ones are not going to make you graph, and we're going to use our imaginations, okay? Parent functions, that means they have not been moved. They aren't stretched or shrunk or reflected, nothing, just the parent function. Imagine constant in your head. Any symmetry, what do you think? There is it even or odd? Even. If you folded it in half, it would go across the y-axis, so that one's even. Imagine your linear parent function. It's going to go through the origin and have a slope of 1. So that would be odds. What's in quadrant 1 goes down to quadrant 3. All right, quadratic, actually already did that one for you. Even, I used that as the example at the top. Square root, so it has a point at the origin and then like goes like that. Yeah, that's neither. There's no symmetry there. Cubic, I did that one up at the top as an example too. What'd we say that one was? That's odd. Cube root, so the point at the origin, and then it's the cubic graph but sideways. So that's also odd. Goes across the origin. Absolute value. It's even, goes across the y-axis. Rational, I'll just draw for you real quick up here. Rational looks like this. It is odd. What's in quadrant 1 goes down to 3, goes across the origin, so that's odd. Exponential is the swoop. That's neither. There's no symmetry there. And then logarithmic is the sideways swoop. It's the exponential turned on its side. Yeah, so that's, if this one's neither, that one's going to be neither as well. So that's even, odd, and neither. Symmetry. Cool? Again, symmetry is important because when you're graphing, it saves you work. If you can find one point, then you know where the other one's going to end up. That saves you time. All right, this is evaluating. I might skip a few so that you can still have some time at the end, but I want you to understand how to do this. This is plugging numbers into a function. So when it says f of 4, 4 is your input. You're going to see what you get as an output. So we're going to take 4 and plug it in for x. I'm going to just do this verbally with you because I don't want you to have to write it out every time. You certainly can if you want, but I don't want you to have to. We're just going to plug in 4. Ready? -3 times 4. Good. -12 plus 7. That's the answer. What that means is the point 4, -5 is on that graph. And if I made you graph it, that point would be on there. Let's try this one. -1. If you plug that in, -3 times -1 to be 3 plus 7 is 10. If you're like, that's it, yep. But you have to be able to mentally do that because you're not going to get cut. Where's the negative for this? On the outside. That means you are just going to negate the whole thing. So I am going to write this one out so you can see what's going on. You're going to put a negative out front and then just copy the entire function over. It's just the whole thing. And you can think of it as distributing the negative, but everything is just going to flip-flop. It's the opposite of what you have. Basically, you're writing what the odd function would be. Okay, so that's going to give you a positive 3x minus 7. It's just like opposite day. For this one, you are plugging -2x into the function. So like when we did this one, you know how we took out the x and replaced it with a 4? You're going to take out the x and replace it with a -2x. So it's going to look like this. So where there was an x, I put a -2x. That's your input. And then you just see what you get. Don't try to force it to turn out to anything. It's just what you end up with. Well, when you multiply these, that's going to be what? Get 6x plus 7. And then that's your answer. That's it. Just use parentheses. Give everything a hug when you plug it in. And then this one, you're just going to take this function and add 2. So if you take this and just add 2 to it, you will get -3x plus what? 9. It's just 7 plus 2 is 9 is literally all the math that we did there. I don't think I'm going to make us do every single one of these because here you're just plugging in numbers. This is exactly what we just did on the other side of the paper with plugging in -x. Let's just do 17 and 18. Okay. Do you see the 3? Where is it? Outside. So you're just going to take 3 times the whole function. So in that blank parenthesis I left, I'm just going to copy over the whole thing. And then you're just distributing the 3. You're just tripling everything. So what would that give you? Multiply the 3 through there. So 6x squared, good, minus 12. Perfect. And then 18, just as a heads up, is the hardest one on there. That's why I saved it for last. Because you're plugging in an x minus 6. So where there is an x, you're going to remove that and replace it with x minus 6. So it's going to look like that. So just as a heads up, this one's going to be a little bit more writing, but I believe in you and you're going to be fine. So whenever you see a squared, I call that a twin. There needs to be 2 of them. So just off to the side here, I'm going to write x minus 6, x minus 6, just so I can see it visually. If you can do that in your head, you don't have to write it. It's not like a necessary thing, but I just put it there. I'm doing the problem in front of a whole group, so I tend to just write everything. So we've got our 2, put a parenthesis. We're going to distribute all this to each other. I call it FOIL, first, outside, inside, last, to stay organized, but basically it's just a bunch of distributing. Here, I'll talk you through it. X times X. X squared. Very good. Now, if you multiply the outsides, you will get negative 6x. Coming with me there? If you do the insides, you will get negative 6x. So negative 6x and negative 6x together is negative 12x. And I didn't leave myself enough room, so I'm gonna have to move over that parenthesis. And then the last, negative 6 times negative 6 is positive 36. I write too big. So we just distributed everything together. Let me recap it. X times X was X squared. Negative 6 and negative 6 is negative 12. We've got negative 12x, and then negative 6 times negative 6 is 36. Are we still together? That was the hardest part. So if you followed me through that, you're good. You're going to distribute the 2. I believe in my heart you can multiply by 2. That'll give you 2x squared minus what? 24x, good, plus 2 times 36, 72. Minus 4. And so your last step is to combine the 72 minus 4. If you're writing with pencil, you can just erase and fix it so you don't have to write the whole thing all over again. So what is that, 68? That one's like a little bit more writing, but you'll be okay. For the last ones, when you evaluate with a graph and you're going to have to watch, I don't have a better explanation than, here, look. There's the answer, which is kind of cool because there's no work, but you have to look, okay? This says f of negative 5. You're going to look along the x-axis for negative 5. Don't do anything else. Just watch me point to this. Do you see how negative 5 is right here? Okay, now I'm going to follow negative 5 until I hit the graph, and all you need to do is see where that matches up on the y-axis. So where does that match up on the y-axis? 4 is the answer. That's it. There's no work. But you have to be able to see that visually, which can be hard. So let's try a couple more. Negative 2. When you find negative 2 on the x-axis and then follow it to the graph, where does that match up on the y-axis? Negative 2. In other words, it's the point negative 2 comma negative 2. All right, and then how about 3? Here's 3. When you find that on the graph, negative 2. Because this little piece is constant, so it's still at negative 2. 4 is a little bit tricky because there's a jump there. It's called a jump discontinuity. We're going to get into that later. Where's the actual filled in point, though, for 4? 1. Do you see that right there? That's the actual filled in point. Is it 1? It's not where the open circle is. And then the last one's 7. So find 7 on the x-axis, follow it to the graph. Where does that match up with on the y-axis? 4. Good.